next presenter is Clint Leeper. Clint had the opportunity 2 summers in a row to participate in the North Dakota Cloud Modification Program, the cloud seeding program in western North Dakota. So he got to spend his summer. He got paid to watch thunderstorms and look at hail and stuff like that. So, you know, it's a pretty cool summer job, actually. But I think that piqued his interest in the climatology of extreme events like large hail and also heavy rains. And so he wanted to kind of see if there's a relationship between that and any other long-term climate patterns. So I'll let Clint explain.
Thank you, Mike. So my actual project that I used for the actual title is a study into the frequency of extreme weather events in North Dakota. So a little bit of background information in this. Global temperature has increased over the course of the last century. This can be attributed to a multitude of things, but the main thing behind this is global warming. We, as scientists, should all understand that global warming has increased in various forms, so we know that that is for sure happening. The Intergovernmental Panel for Climate Change is speculating that there will be an increase in the number of extreme events in relation to this. So, and to back this up even more, the National Wildlife Federation states that an increase in extreme events that used to happen every 20 years are now occurring every 6 years. So, how much has the temperature actually increased over the last 20 years? Well, the average temperature increase for the departure from the 20th century looks a little bit like this. For North Dakota, there's been an increase of about 1 to 2 degrees. And it's actually across most of the country there's been an increase in 1 to 2 degrees. The Northeast has seen an increase even as far as 2 to 4 degrees. What's most interesting also about this fact is that you can kind of see how it changes in periods over the course of groups of states all at once. They go, you'll have a multitude of states that actually start to have an increase in temperature, reporting there's been an increase over the departure from the 20th century average. And a little bit more into this is how the extreme events actually correlated to that. Well, you can see here that the actual number of events has, or this chart actually displays the number of events from 1993 to 2012 with the respective years with them. And it also classifies what kind of event it is based on the color. What's most interesting about this graph is that North Dakota and South Dakota and much of the northern plains are actually missing from this data. And part of my reasoning behind this, I speculate, is that since there's not a very dense population, there's not the number of places for people to actually report the data. Since a lot of these events are going to be convective in nature, they're going to be very short-lived events that are going to dump a lot of precipitation and then dissipate again before it actually hits a major body population center. So what I went ahead and looked at was for observations, I used the North Dakota Atmospheric Resource Board Co-op Weather Observer Network. Each year there's around 850 different stations, and each station there's 2 different types of them. One's going to be a year-round report, and they report things like snowfall, rain, and hail, and then the other kind is summer only. The summer only reporting stations only use data from April 1st to September 30th, or essentially whatever the growing season is for that year. We're going to be looking at events that are going between April 1st and September 30th for this case study, and it's going to be assumed that cases are over a 24-hour period. So it's going to be the total amount of precipitation over 24 hours for the total for that day. So just to give an example of what the observer station looks like, this is the 2015 map of all the stations in North Dakota. The least densely populated station area is Sioux County, which is in the lower portion of the state, and it still has 4 stations that report over the course of the summer. One of the benefits of using the observer network is that you don't have to use AWOS or ASOS station data. So you don't have to worry about it only being just at a runway or an airfield like that. You have it anywhere it could be. It could be at anyone's farm and report station. It's all a voluntary network. So my actual hypothesis for this statement is that the increase in mean temperature in North Dakota causes an increase in the frequency of extreme hail and rain events. So we're going to look at a total of 5 different grades of hail data. Grade 0, it's worth mentioning, is going to be an unknown size. Now, why it's unknown, it can vary. It could be just that something wasn't reported for it, the hail melted too quickly for it, or it was too dangerous for a person to run out into the middle of a hailstorm and actually be able to report that hailstone size so we can get an accurate measurement on it. What we're going to be looking at specifically during this study, or we're going to be looking at grade 3 and grade 4 hail cases. So over these over the period of this, we're going to be looking at 8 periods of rain events and 6 periods of hail events. We started with hail events starting from 1985 and going through 1989, which is 2 periods later than the rain events, because hail data wasn't reported frequently enough until 1985. So that was when they first started reporting it annually and everything and consistently. But otherwise, most periods last for about 5 years. The only 2 exceptions for that are the beginning of the case study, which they last from 1977 through 1979, which is the first year, was 1977, and then 2010 through 2015, so that way we could use all the way up through last year's hail data and rainfall data, so that it could be the most recent. So, what is going to be classified as an extreme event? Well, I kind of foreshadowed this a little bit, but a hail event is going to be anything that meets or exceeds a grade 3 event. So a grade 3 is anything that's over 3/4 of an inch or larger. Grade 4 is going to be anything that's over 1.5 inches. What's worth noting here is that this was based off of the National Weather Service old standard for a severe thunderstorm warning, where anything that was greater than 3/4 of an inch constituted a severe thunderstorm. Since this project first started, they have actually increased it to being 1 inch, and they've never updated it for the atmospheric resource report, so they still use 3/4 of an inch. And there's no actual reporting. It doesn't give the actual dimensions when you're reporting on the cards of what the hailstone actually was. So grade 3s and grade 4s are still an accurate representation. So this is the actual frequency of events for a grade 3 storm. On the y-axis, you have the period starting from 1985 to 1989 in each subsequent period. And then on the bottom, you have the normalized value for these events. The normalized value for these are going to be the number of events over the total number of stations for that particular period. So you can see that there's a very slight upward trend in the number of events. The slope for the actual value for this is 0.0014. So like I said, it's very, very slight upward trend. And I've only got an R-squared value of 0.02. So that could have a little bit of an effect on things. For grade 4 hail frequency, so anything over 1.5 inches, you have a slight decrease in the number of events. In this case, it's actually minus 0.0025, but the R-squared value has increased on this one a little bit to 0.16. And again, the chart is set up the same way, with periods being on the left-hand side, and then on the bottom being the actual normalized value total. So now that we've talked about hail, I'd like to talk about precipitation. So we have to, again, establish what makes an extreme event extreme. For events producing greater than 1 inch of precipitation, the average precipitation value is 1.511 inch. Now, like I said, I wanted to really focus on extreme events, so I started off with not including smaller values and doing anything greater than 1 inch to begin with, because I wanted to focus again on the heaviest of the heavy rainfall events. Whenever I calculated the average, or this average of 1.511 of an inch, I ended up getting a standard deviation of 0.59 of an inch. Classifying anything as being 2 standard deviations or greater being extreme, you end up getting a total of an extreme event being anything that's greater than 2.68 of an inch. But like I said earlier, I really wanted to look at the extreme of the extreme rainfall events for this. So for this study, I looked at events being anything greater than or equal to 3 inches of precipitation in a single 24-hour period. So just to put things in perspective, these are events that are less than the extreme trend. This is a graph of the precipitation values from 1 inch to 1.99 of an inch. And it's set up the same as how the hail data was set up, with period being on the left-hand side and the number of events and the number of stations, the normalized value for that, again, being on the x-axis. And you get a slope of 1.2544 for the period of events, and an R-squared value in this case of 0.8498, which is a significantly better R-squared value. And even more comparison, for events that are between 2 inches and 2.99 of an inch, you get a significantly less slope, but still an increase nevertheless of 0.1782, and an R-squared value of 0.82. So again, a very accurate representation of it. What's most interesting is that the cases haven't or increased significantly, and then they have a slight decrease in them, and then they continue to increase again. It's worth noting that between 2000 and 2004, there was a nationwide drought, so that's the reason why there's this big drop in the number of events. So, like I said earlier, I looked at events that were greater than 3 inches of rain. I wanted to look into the extreme events for this, so I broke it down into 2 categories. Events that were between 3 inches and 3.99 of an inch, and events that are greater than or equal to 4 inches. 4 inches, or the greater than 4 inches, are going to be anything that are 4 inches, 5 inches, 6 inches, even to the most extreme case, which is around 10 inches of rain in a single day. So for values between 3 inches and 3.99 of an inch of rain in a single day, you get this kind of graph. The normalized values for this show that there's been a significant increase in the time, with a slight decrease from 1980 to 1984, and then again in 2000 to 2004 with the drought that I earlier mentioned. But you still get a slope of 0.0282 of increase over each period, and an R-squared value in this case of 0.65. So R-squared values are starting to go down a little bit in this case, not being quite as representative of the data that it should be, but it's still a significant R-squared value. For events that are greater than 4 inches, you see a R-squared value of 0.4698 and that slope of 0.0103. And again, a significant increase in the number of events. So looking at everything in a combination of all extreme events, both hail data, which is grade 3 and grade 4 hail data, and looking at rainfall events that are anything that are 3 inches or greater, you can see the number of events has increased on almost every case except for the grade 4 hail data, which is actually, like I said earlier, has that slight decrease in it. So how frequently is this? Like, how many actual events do we have each year where we have a grade 4 case that actually occurs? And this is over the period of events. So like I said, it's 5 years. And you only end up getting a total of around like 63 cases over the period of 5 years. So that's less than about 12 cases or so for the first period, and it still doesn't. That's actually the most significant number of events for the entire study, or for this entire case study. Precipitation values, again, it's similar to that. It is worth noting that the total number of stations has increased, but then again, it begins to decrease. But what doesn't change is the number of events that occur. So even whenever you have 2010 to 2015, where there's only a total of 717 stations for that period, you still have over 74 cases of 4 inch or greater precipitation values, which is more than the number of cases that occurred from 1985 to 1989, where you have only 51 cases for that. So it's just an interesting case. So what's my actual conclusion for this? Well, it's clear that there's been an increase in the number of extreme rainfall events. That's clearly present. The average increase for non-extreme events is around 300.5%. That's occurring. And the average increase for extreme events is still 186%, so it's still clearly increasing. When you total those together and take the average of that, you still have an increase of 243% of both extreme and non-extreme rainfall events. But for hail, it's a little bit different of a story. There's no clear trend with hail. There's a slight increase in the number of cases that occur over a grade 3 category, but it's very slight. And even if you do say that the number of cases has increased for it, grade 4 frequency decreases by double the amount of slope per year. So what future work I think that needs to be done is, if we're continue on with the study, you'd want to look and see if the number of grade 1 and grade 2 hail events has actually increased, and see if there may be similar to what happened with the number of extreme rainfall events, if that number also increases for non-extreme hail events, and see if there's a correlation between the two of them, or see if there's any kind of correlation at all. Other than that, I just have a few acknowledgments that I'd like to make. Both Mike and Mark for being the chairs and committee members for my project, and Nick Gapp for helping me get my code to work. Thank you, Nick. I owe you for that. And Mark again for letting me ask 1 million questions. That also goes to Mike. And then Mac and Samantha Edwardson for reviewing my paper, giving me advice on how to improve and change a few things. And then also Jenna Weinberger for being there and supporting me and listening to me talk about the also exciting world of extreme rainfall and hail events for the last year. And if you're interested, here are my references, both for the Intergovernmental Panel for Climate Change, a few different editions for that, and information from the NCDC, which I can't remember what that acronym stands for. But yeah. Are there any questions? Yes.
I know you touched on it a little bit. In 2000, 2004, there was a severe drought. Are there any other climatic impacts in any other time frame that were worth noting?
Well, there was the flood for 97 for Grand Forks, but that was only a small portion, as well as the flood for Minot in 2010. I'd like to look into those cases a little bit more and see if there's anything that's more localized data, not over the course of the entire event. So that's the reason I didn't really focus in on those points. Yes, Leon.
Two questions for you. First, with regards to your normalization, can you explain again how you normalized your data?
I did the number of events that occurred for over a period of time for that period. So let's say it's from 1985 to 1989, and I did the total number of stations for that time period. So the total number of stations from 1985 to 1989, and I took that value.
Okay, so with that as your method, what's some of the potential error you could see in that result?
You would have stations that no longer were part of it, that may have left mid-period, which is one thing that I know that's where it's allowed, but you also have stations that are introduced during that time period as well. So that's one thing that you could have. Off the top of my head, I can't think of a second one.
One of the other problems is, since you selected a 5-year period, I agree there are some that come and they go. It would be interesting if you had seen it. So, for example, in I think 2010, 2015, it was 711 stations.
Yep.
Was that by taking each of those years, that's the average number of stations over that time period? Okay, 717.
Yeah.
Is that the average number of stations?
That is the total number of stations. So what I did for that is I went through Excel and I did a remove duplicate for that time period just to see what I could get for a total number of stations that way.
Okay. The other question is, did you look at the variability of reporting by those stations? Because one of the issues,
Yeah.
being an individual that reports, I know there have been times when I've been gone.
Yep.
And I've not made the report. Is any way of looking at the errors induced by missing major events?
Yeah, that is something that I thought about too whenever I was doing this, was the number that you would have for, periods where you have people that don't report or something like that. And you also have the case of someone not accurately reading the rain gauge, or the rain gauge not being in the correct spot. Since there's no way of actually controlling that, I had to take it in, I guess, good faith that they accurately reported it, or the event just wasn't reported and was given a null.
Okay, so do you see any way of estimating your error then? And would that error influence your result?
I'm sure there's a way to look into it and see if the number of reports, I could cross-check with storm reports in the case of hail. I could see if that hail report was reported, because the stations are, of course, with latitude and longitude. So I can look and see if there's another hail report with that same latitude or longitude. And there being a significant number of stations that are missing, so they miss event, that error calculation, I don't think would be great enough to actually to really change the results overall, with the period of events, especially for rainfall, which has been going on for 38 years. Hail data is a little bit more susceptible to it because it's only been going for 30 years. So I think the best way to fix that would be just look at it over a longer period of time and see if that would help eliminate some of those errors.
And if you'd indulge me, one other question.
Yep.
You are relating precipitation, extreme precipitation and hail events to increase in temperature. Now, part A, why just temperature? Now, why couldn't you use the number of vehicles traveling on I-94? I mean, it seems kind of arbitrary. Why temperature? And the other is, do you have any type? Did you look at any type of synoptic basis?
I did not look at a synoptic base for it. I didn't look at a causation other than just looking at, since there's been an increase in temperature, what's the increase in temperature, if there's any correlation to it, so, and to the number of events.
Okay, so with that, I mean, could I pick something else and had the same results or better results? It seems rather arbitrary to be able to say that, well, okay, increased temperature, you're going to get more rainfall without attaching it to some type of physics. We all like statistics, and we know we can always make statistics do what we want. So I'm a little confused as to how this necessarily relates to temperature.
You had that in your paper, so what did you decide the physics were?
Because there's an increase in the temperature I looked at, there's an increase in the available potential energy, so an increase in Cape values for it, or am I going down the wrong pathway?
That's a possibility, depending on how it's distributed.
Yes. Yes, Gretchen.
So, when you were looking at your linear regression, particularly when you have very few points, which you don't have very many points.
Yes.
Like you have a lot of years, but you averaged over, so you end up with just a few points left.
Yep.
Where you end, like which years you end on can make a big difference in the line that you end up with. So did you do any looking into, like if you cut off like the last period, did it change, how significantly would that change your regression line?
I didn't look into changing like when the periods ended. I always use the 5 just because I figured that would be the best average using the half decade. Can you elaborate more on your question, I guess?
Well, so I guess your answer is no, you did not investigate
Yeah.
that. So instead, this becomes a comment that if you were to continue with this work, that would
Okay.
be useful because, does that make sense? Like if
Yeah,
you
we'll
look at the
change it.
graphs you made, particularly because some of the more recent 5-year periods had actually decreases, it can actually significantly impact when you have few data points where you begin and end your regression. So it's just something to be aware of.
So change it just so.
Well, if it's very sensitive to that suggests that maybe you need to approach your data in a different way.
Okay.
Because it doesn't mean, it means the result's not very robust, right?
Yeah.
Yeah, I would comment, I would just, instead of breaking into periods, just do it every year. You're going to have more noise, because there'll be more year-to-year variability, but see if you end up with the same trends.
Yeah.
That's, you're going to see in that last 5-year period, was there one anomalously high year that's skewing everything, or not?
One question.
Yep.
Look like your stations varies from 5 year to 5 year, right? Some
Yep.
year you have more stations, some year have less stations.
Yep.
This really introduces something bias. Have less stations, less,
Yep.
have less detectability. So, is there any way you can reduce this kind of sampling bias by modifying your approach?
Well, that's the reason why I did the normalization of the different stations, so that way I could always get a value that's consistent at least. So that way that even though there are periods where there's 1,100 stations, the number of events don't really increase, even with the number, or I guess they do increase, but they don't change drastically, because even whenever you have times where there's 717 stations, I still get a number of events that are still greater. Yes.
How many of those stations were in existence every year of your study?
Beginning with the 1977 ones, there's been a total of, I think, 40 stations that have made it for the last 40 years. Some stations go on reporting with different people, and it never gets notified. Some quit reporting and then come back and they get assigned a different number. So that's something that also changes.
Is there any geographic bias in how the stations were added or removed to the network?
I think they're added or removed simply by who applies for it. That's my understanding of it, at least. So,
Because if you had one region of state have a mass loss of stations compared to another, that could introduce some significant concerns into.
that's also true.
I ask one more question. Have you checked the frequency distribution with respect to spatial distribution? Around North Dakota, east versus west?
I wanted to see the spatial, and I was attempting to do it on ArcGIS to do a map, and I was actually going to bring it up here, but when I renormalized the data, it was later on, and honestly, I just ran out of time to go ahead and do a spatial distribution. It's something for further work that I'd like to do, is that I'd like to break it down into different regions, and see if the western side, break it up basically into what major city for that population, and see if each region has its own like increase in the number of events or if it's decreased. So, Ben?
I have a comment and a question. My comment is, I do like your study that you're focusing on extremes, but the one major weather extreme that's important, or I should say is worse than actually rain and hail, is heat and heat waves. So I think maybe in future work, you could maybe look at that as well, especially since you're trying to connect these with increasing temperatures. So like, maybe are heat waves increasing? Are they stronger? Like, I shouldn't say stronger, but are they warmer? So I think that's something you could look at. But my question is, what societal impacts do your findings have?
Well, especially whenever it comes down to like floods and economic like losses and whatnot. Well, an increase in the number of hail events like that, as a lot of people know, the whole reason why the North Dakota Cloud Modification Project is in existence is because of the high crop insurance costs for the western part of the state. So that's one economic thing for it. And then the number of extreme events, especially when it comes to terms of flooding, there's a large economic loss, monetary. This is going to be a little bit different, but the number of the flood of Grand Forks in 1997, I can't remember 100% what the number is, but I have something like $3 billion. I'm sure Leanna can correct me on it, but there was a huge loss for the state, not only in revenue, but also the cost of replacing and drawing all that, and the later crop yield and crop end dates and stuff like that. So that's something that can be an effect. Yes, anyone?
Since this is part of the North Dakota Atmospheric Resources Board, and we know that their weather modification is to suppress hail, the fact that you're seeing this variability, what can you say about the success of that program in preventing grade 3 and grade 4 hail events?
For the success of the program and the variability of that, it comes down to what states or what counties are actually part of that, and I think that would be better answered if I were able to break it down into the different regions.
Okay, I agree.
So that's the reason why I haven't went into the different region, or that's a future study to see how the counties that are in the project and when they leave the project, if there's a relationship in the number of hail cases that they have.
And I think Darren Langeroo would like for you to be able to separate those out because to help himself tell his story.
Yep. Any other questions?
Okay, thank you.